Earthquakes are a powerful force of nature. They can cause widespread destruction and loss of life. Understanding seismic risk is crucial for protecting communities and building resilience. In recent years, there have been significant advancements in the field of seismic risk assessment. Scientists and engineers are now able to combine data from multiple disciplines to create more accurate and reliable risk models. This essay will explore a unified framework for seismic risk assessment. This framework integrates geology, seismology, numerical analysis, and statistics. By combining these disciplines, we can gain a more comprehensive understanding of earthquake hazards and their potential impact. This knowledge is essential for developing effective mitigation strategies and building codes. Earthquakes do not respect borders or boundaries. A seismic hazard in one region can have cascading effects on others. Therefore, a global perspective is essential for understanding and mitigating earthquake risk. This unified framework provides a common language and methodology for scientists, engineers, and policymakers worldwide. By working together, we can use this framework to create a safer and more resilient future for all. Traditional approaches to seismic risk assessment often focused on individual disciplines. This approach resulted in a fragmented understanding of earthquake hazards. The unified framework addresses this limitation by integrating data and methodologies from multiple fields. This approach provides a more holistic and accurate picture of seismic risk. Geology plays a crucial role in understanding earthquake hazards. It helps us identify active faults, assess their potential for rupture, and characterize the near-surface geology. Seismology provides insights into the earthquake process itself, including the magnitude, location, and frequency of past events. Numerical analysis allows us to model the ground motion caused by earthquakes and its effects on structures. Statistics help us quantify uncertainty and estimate the probability of future events. The unified framework integrates these disciplines through a process of data synthesis, cross-disciplinary calibration, and merged models and analyses. This integration allows for a more comprehensive and robust assessment of seismic risk. The foundation of the unified framework is the synthesis of data from various sources. This data includes geological maps, earthquake catalogs, ground motion prediction equations, GMPEs, GPS velocity fields, and statistical analyses. Geological maps provide information about the distribution of different rock types and the location of faults. Earthquake catalogs document the history of earthquakes in a region, including their magnitude, location, and depth. GMPEs are mathematical models that predict the intensity of ground shaking based on factors such as earthquake magnitude, distance from the fault, and local soil conditions. GPS velocity fields track the movement of the Earth's crust, providing insights into the accumulation of strain along faults. Statistical analyses are used to quantify uncertainty and estimate the probability of future events. The data synthesis process involves collecting, cleaning, and standardizing data from various sources. This process ensures that the data is consistent and reliable. Once the data is synthesized, it can be used to develop a more comprehensive understanding of seismic hazards. The devastating Turkey-Syria earthquake of 2023 highlighted the importance of accurate seismic risk assessment. This earthquake, which resulted from the rupture of the East Anatolian Fault, caused widespread destruction and loss of life. The unified framework can be used to analyze and learn from this tragic event. By combining geological data, fault geometries, and ground motion models, the framework can help us understand the factors that contributed to the severity of the earthquake. The Coulombic stress transfer, CST analysis, a key component of the framework, can show how the earthquake increased stress on nearby faults, potentially triggering future events. The Turkey-Syria earthquake serves as a stark reminder of the destructive power of earthquakes and the urgent need for effective risk mitigation strategies. The unified framework provides a powerful tool for analyzing past events and preparing for future ones. Section 5 Case Study: The 1999 Izmit Earthquake. The 1999 Izmit earthquake in Turkey provides another valuable case study for the unified framework. This earthquake, which ruptured a segment of the North Anatolian Fault, caused significant damage and casualties. The framework's ability to integrate geological, seismological, and numerical models allows for a detailed analysis of the earthquake's characteristics and impacts. By studying the fault rupture process, ground motion patterns, and building responses, we can gain valuable insights for improving building codes and emergency response plans. The Izmit earthquake underscores the importance of considering regional seismicity patterns and the interconnectedness of fault systems. By studying past events, we can better understand the potential for future earthquakes and their potential impacts. Section 6. Outputs: Visualizing Risk and Uncertainty. The Unified Framework produces several key outputs that are essential for communicating seismic risk to stakeholders and decision-makers. These outputs include hazard maps, fault reactivation probabilities, and risk scenarios. Hazard maps depict the spatial variation of ground shaking intensity for a given probability of exceedance. These maps are essential for land use planning, building design, and emergency preparedness. Fault reactivation probabilities estimate the likelihood of a particular fault segment rupturing within a specific time frame. This information is crucial for assessing the vulnerability of critical infrastructure and developing targeted mitigation strategies. Risk scenarios combine hazard information with exposure and vulnerability data to estimate the potential consequences of future earthquakes. These scenarios help policymakers and communities prioritize mitigation efforts and allocate resources effectively. By visualizing risk and uncertainty, the Unified Framework enables informed decision-making and promotes proactive risk reduction measures. In Section 7, Synergy and Reduced Uncertainties. One of the key advantages of the Unified Framework is its ability to reduce uncertainties in seismic risk assessment. By integrating data and models from multiple disciplines, the framework provides a more robust and reliable assessment of earthquake hazard. The cross-validation of data and models from different sources helps identify and address potential biases or inconsistencies. This process leads to a more accurate and defensible assessment of seismic risk. The integration of multiple lines of evidence also allows for a more comprehensive understanding of the uncertainties associated with seismic hazard assessment. This understanding is essential for communicating risk effectively and making informed decisions about mitigation strategies. The Unified Framework promotes synergy among different disciplines, leading to a more holistic and rigorous approach to seismic risk assessment. Section 8. Policy Implications and Building Codes. The outputs of the Unified Framework have significant policy implications, particularly for building codes and land use planning. By providing accurate and reliable estimates of seismic hazard, the framework enables the development of building codes that are tailored to the specific seismic risks of a region. Building codes are essential for ensuring the safety and resilience of structures during earthquakes. By incorporating the latest scientific knowledge about seismic hazard, building codes can be updated to mitigate the risks posed by earthquakes. The Unified Framework provides a sound scientific basis for developing and updating building codes. This ensures that structures are designed to withstand the ground shaking expected in a particular location. The framework's outputs, such as hazard maps and fault reactivation probabilities, can also guide land use planning decisions. By identifying areas of high seismic risk, policymakers can make informed decisions about zoning, infrastructure development, and emergency preparedness. Section 9. Conclusion: A Safer Future, Built on Knowledge. The Unified Framework for Seismic Risk Assessment represents a significant advancement in our ability to understand and mitigate earthquake hazards. By integrating geology, seismology, numerical analysis, and statistics, this framework provides a comprehensive and robust approach to assessing seismic risk. The framework's outputs, including hazard maps, fault reactivation probabilities, and risk scenarios, are essential tools for policymakers, engineers, and communities. These tools enable informed decision-making, promote proactive risk reduction measures, and ultimately contribute to building more resilient communities. The devastating earthquakes of recent years serve as a stark reminder of the importance of earthquake preparedness and mitigation. The Unified Framework provides a roadmap for a safer future built on a foundation of scientific knowledge and collaboration. By embracing this framework and working together, we can reduce the risks posed by earthquakes and create a more resilient future for all.